Okay, so let's continue. So Tilo is set up so that I can switch between the blackboard and this now. Let's see. Okay, so we saw demographic random variables. So now we come to this this notion called statistics, right? So statistics is a very well-defined concept now. So here are some sites on government statistics of New Zealand and Sweden. So official statistics data we can fetch from there if we want to get into some socioeconomic data sets. So what I'm going to next define is data. Okay, so this is again a choice from my point of view. It's a personal choice. I want to define the data space. It'll make things easier down the road in machine learning. So in general, given some probability triple omega fp, let the function x measure the outcome little omega from the sample space like this. So this is just our usual random variable. So we're going to call this x our data, okay? And bold x, or map blackboard font x, which is the space where data gets realized, doesn't have to be real valued alone. It doesn't have to be a vector of real valued. It can be very general. It can be, you know, movies or sounds or whatever, videos. It could be all sorts of things. Right? As long as it's measurable, we can record it, measure it. It's basically what I mean by the data space. So this is the data space, and the random variable that maps from the sample space, sort of reality model, to map bbx is data. So in other words, x is the finest available measurement of the sample space. Okay. So then x of little omega is lowercase x. So this means there is a realization of little omega, and this realization is little x, right? So this could be, this is usually what we work with. Yeah, so it could be trajectories of cell phones of peoples all over Scandinavia for the last decade, right? This is actually a data set that John talked about. And of course, you know, that sort of finest resolution may be available to certain data collectors or data controllers. The particular data set, you know, John was talking about in this setting has ethics approval for this region, the Uppsala region, because they confidentialized it by changing the IDs of the cell phones every so many hours. And then they also don't allow the resolution of the cell phone to be anything more than a tower. So it's much coarser representation. So those would be, in fact, that may be the data space you will be working from. It doesn't mean that a security agency can't get much more information than that. So these are, you know, so different group of experimenters may have different access to the same, you know, same omega. Right? So NSA has quite a lot of access. Right? Okay. Yeah. So real valued random variables, and we can have real valued random vectors. And for us, that's pretty much enough, because an image, you know, a color image is what? It's just a bunch of pixels, right? And in each pixel you have RGB values, and the RGB values will be some number, right? If it's grayscale, it's some number between 0 and whatever, 200 and something. If it's it's a color image, you would just have the RGB values, so it'll be a triple, and each of those values in the triple will range in some integers. So they're actually just random vectors, right? Real-valued random vectors. Same with MP3, sounds, all sorts of things. So often it's enough to just think about real-valued random variables. Oh, by the way, next Friday, we will do whatever we can, okay? But the recommendation, or my strong recommendation is, there is a seminar, right? There's a colloquium next Friday. This is one of my two advisors, right? His name is Michael Nussbaum. So he will be working with complex valued random variables from
well, even worse, you will be working with quantum random variables.
So that's kind of the culmination of this. You don't have to go, but I strongly encourage you to go, because you are going to start seeing the Nyman-Pearson lemma, which is the simplest test you could do of two hypotheses for quantum physics or quantum statistics. So that's pretty much sort of dropping you on the almost cutting edge, right? A few years old annals of statistics work. And it's a colloquium talk, so it's good to go, and it's included in the up to 5 p.m. time. So technically you should go. I think it starts at 3:15, and there's some fika there. So I will finish next Friday before that, for 3:15. And it'll be good for you guys to see Michael's talk. Okay, so what is a statistic now? A statistic is just any measurable function of the data. So we formally say T, capital T, is this random variable. T is actually a random variable that goes from the data space to the statistic space. It's for the specific statistic T. Okay, so we write it as T of lowercase x takes the value little t, right? So the random variable capital T of the little x takes the value little t. This is often called the observed statistic, right? So yeah, you sort of write like this in short notation. Random variable t maps the data space to the statistic space. And of course, the sigma algebras are still there under the hood, propagating all the way from the sigma algebras in the sample space, at least conceptually. So we also can denote it this way. Lowercase x maps to t. So when the experiment is done, the data crystallizes into little x, and then the statistic maps that little x into little t. So here's a basic question. Can statistic be the data?
Yes.
Yeah, why not, right? So if t of x is itself, then then basically statistic can be the data. So here's the so it's if you have the identity map t of x equals x, then essentially you have the statistic space becomes the data space, right? I don't know, I try to do this little hiding the answer here. Okay, so yeah, data can also be just the statistic. So this is what we want to really remember as an experimenter. You are thinking of x mapping the sample space to the data space and some statistic t mapping x to t. And these are the realizations going, right? Omega little x little t. So why is statistic important? One of the most important things with statistic is that for a particular decision problem at hand, so we'll hopefully get to some example decision problems. It could be parameter estimation, it could be hypothesis testing, any of these simple problems engineers and scientists face all the time. You may not need to know all the information in X. You may not need to know all of the data. You may only need to know the data up to some projection, right, to the statistic, which often is many-to-one mapping. So various little x's will be the same t. When you can guarantee this for the decision, it's enough to only look at the statistic, then the statistic becomes often what's called the sufficient statistic. So Yeah, this is just a recall of everything. So we have observable events in the sigma algebra f of omega on omega that are captured by the random variable x as measurable sets in f of x, sigma algebra over the data space x, and typically projected further by the statistic t, which is just another random variable that measurably maps the sigma algebra f of x to the sigma algebra f of t. Okay. So here, let's look at this New Zealand lotto data. So this is just the first ball drawn from a New Zealand lotto machine. So I just put the whole list there instead of processing it. We'll process it live downstairs for New York. So the length of that list is 1,114. So there's 1,114 draws over several years. So here, concretely, what is the data space? So this is just now like looking at all possible sequences of ball numbers that we could have gotten in these 1,114 draws, right? So that's basically written like this. So you raise a set, a finite set to a power. It just means a Cartesian product. So that means the first element could be one of the 1 through 40, the second element could be one of the 1 through 40, all the way down to the 1,114th element. So which means you have 40 to the power of 1114 possible sequences in this data space. So if, I don't know, it's not a great example in a way, but you know, if the world was sort of rerun and the lotto balls popped out again, it could be another X in that space. So the probability model we're going to use is this de Moivre random variable, right? So we have x1 through x1114 are my measurements now because I'm measuring by this real number, which is the ball label, 1 through 40. And my model is this tilde means distributed as, okay, and this IID stands for independent and identically distributed as. That means each trial is independent of the previous trial and or the next ones, and then they're all distributed as this de Moivre random variable, right? This 1 over 40 equiprobable case. Okay, so so the probability of the data is actually now 1 over 40 to the power of 1114, right? It's 1 point. This space. So that's concrete example of a data space. Now some statistics are sample mean, right? So I basically, sample mean is usually denoted by this x sub the n over bar. It just is a standard notation for sample mean. And, oops. Oh, page down works differently here, too. I don't know what's happening on the board.
You want me to switch?
Oh, I don't know.
I mean, page down will still react in other programs. The problem is just that this sends page up and page down. So
I see.
This is why we have to use page up and page down.
Oh, I see.
But I've switched over, so it's on the board now. So.
Okay. Yeah. So I mean, this is something to. This is again standard notation. Remember, we talked about the expectation of the random variable x. That's called the population mean. But then, if you have a finite sample, x1 through xn, then xn, these are now IID from some distribution f. Let's say then this notation x sub n over bar is standard notation for the sample mean, which is 1 over n times the summation of x1, xii goes from 1 to n. Right? So the sample mean is random, right? It's a random variable. It's a statistic. Okay. That means every time you repeat this experiment, you get another n to pull, you get a different value of the sample mean. And then we can ask, what is the variance and the expectation of the sample mean itself, right? So that's what this is trying to do. Expectation of xn is you just carry the expectation inside, so it's 1 over n. Something's happening.
Okay. Yes, I'm trying to switch back to you.
All right.
Yes. Okay. Good. Started.
Yeah. So it's basically you just carry the expectation inside, so it's 1 over n, summed where the expectation of each xi is. And of course, all the xi's have the same expectation because they're IID from the same random variable, right? It's a product experiment. So we just have n times E of x1, and that's just E of x1. So this is again just convention, right? Expectation of x1, because all the random variables are IID, expectation of x1 is equal to expectation of x2 is equal to expectation of xn. So you just say it's just expectation of x1, all of them. So it'll just be 1 over n times n expectations of x1. So that's the expectation of the random variable or statistic called the sample mean. Now we can also look at the variance of that statistic. So we again define, find the variance. By variance is 1 over n times the sum. And remember this constant, we have this property, variance. So it's just the squares. So it's 1 over n squared times the variance of each of the xi's. And once again, the variance can go inside, and each of the xi has the same variance, x1. So it's just 1 over n squared times n times variances of x1s. So that's just 1 over n variance of x1, which is interesting, right? So the variance of the sample mean is a lot smaller, right? It's 1 over n times the variance of each xi, which is a nice property, which means, as your sample size increases, the variance of the sample mean decreases linearly with n. Okay, so the next statistic is called sample variance. Right? So sample variance is, this is the definition, it's 1 over n times the, so where you take the squared difference between the random variable xi and the sample mean. Okay, sample mean we can compute, which itself is random, and then we do this, and that gives us the sample variance. Okay. So now we're going to get introduction to Numpy, which is a numerical Python library that's inside Sage. And it's very, very powerful for floating point numerical computing. Right? So we can use this statement here, import NumPy as NP, which means any NumPy object we can refer by just the 2 letters NP. So I'm kind of doing this explicitly now. So I'm going to say I'm importing everything this way instead of specific things. Then I'm going to say array ball1 is my variable. It's going to be np numpy.array of the list ball1. So list ball1 was this list of Sage integers. So I pass that into np array, and I can create a numpy array this way. And NumPy has nice syntax for long things. It just puts ... if the list is too long. So if I now hit tab after the array ball1, these are all my methods available on the NumPy array we just created. It's quite a lot of stuff. This all comes from NumPy. So one of the methods is actually the mean, sample mean. So the sample mean of the New Zealand Lotto, this NumPy array is just this dot mean. And that makes sense, right? That's also mean for the Dumare random variable, which will be our model for it. So if you just call the mean without the parentheses, this is just going to give me this, this built-in method. Right? So we need to evaluate it with the parentheses. So same with variance, you can do variance. This is a sample variance, sample standard deviation, and it's just checking the sample standard deviation is really the square root of the variance using the sqrt function. So next we'll get into order statistic, right? So if I have this big list of 1114 numbers, they are numbers between 1 and 40, and they come in whatever order. I could, for example, order them, right? Or if I just have generally a bunch of realizations of some continuous random variable, I can sort them. And the order statistic is essentially a sort of the data. So we know the minimum and the maximum are here. And so here's how I would do this. So I would create a variable called array ball1 sorted, and I'm simply putting the np dot array and turning this list ball1 into a numpy array, and then I'm going to call the sort method on it, right? So this is because when I actually take an array and sort it, it will do it in place, right? So I didn't want to do it on the original data. If I want to keep the original data, then I'll be in trouble, right? It'll do an in-place sort. That's my order statistic. And because we left the original one alone, it's going to be, this is the exact order in which we receive the data. And then that's just the sorted one. So here's a question. So the order statistic is basically a sorted version of the original data, right? So is this a many-to-one mapping or not? One-to-one. You think it's one-to-one? Okay, what I mean by that is, so let's say we only have three numbers, right? 3, 2, 1. This is the data I got, let's say. Then the sort of that, the order statistic of that will be 1, 2, 3, right? But if I have my original data to be 2, 3, 1, then the order statistic will still be 1, 2, 3, right? So, which means, but let's say this is this is rolling the die example. Let's say I have 5, 6, and 1. This won't go there, right? This will go to what is it? 1, 5, 6. Right? So I'm rolling a 6-sided die 3 times. That's my experiment. So, right. So what is my data space for that experiment? So I have x1, x2, x3, IID, Dumore 1 over 6, 1 over 6s, right? So I'm rolling a fair-sided die 3 times. So what is my data space? What are all possible 3 tuples I can get? Yeah, so the first one can be 1 or 2 or 3 all the way to 6, right? So you just think of a branching diagram. The second could be any one of 6 again, right? Because I'm just rolling the die. So it'll be 6 times 6 times 6 possible values in the data space, right? What is that? 6 are 36. 36 times 6 is what? 180 plus 36 is 206. What is it? 260. Okay. All right, so that's my data space. And now the statistic, order statistic, is now mapping those possibilities into a much smaller space, right? Anyway, if you get into this is basically beginnings of combinatorial probability, right? Anyway, we won't go too far into combinatorics here. So why is order statistic important? Order statistic is very important because for IID experiments, right? That means every x1 through xn is independent and identically distributed. a lot of the information, in fact, all the information, even about the distribution function, is just in the order statistic. Okay? We will see this later in non-parametric estimation. That, okay, so now let's get into. Wow, this
is a bit
annoying, isn't it?
Yes, I will be more careful too. So, because if I match them one to one, it should just go one page down and then one page back up. But,
yeah. All right. So the next main statistics of interest is frequencies, right? So same idea. We basically have a bunch of random variables, x1 through xn, real valued, let's say, or it doesn't even have to be real valued. It can be arbitrary things. It could be just, you know, some kind of random graph realizations, you know, which again possible. Then all we're interested in is counting how often each type occurs, right? Just the frequencies. So that's all this is doing. So now what we want is we want a function to count the elements in the sequence, a generic function to do this for us. Then we can look at any experiment, any simulation, and quickly use this to find the frequencies of items in it. So we're going to make this function called makeFreqDict, right? Make frequency dictionary. And its input is going to be my data sequence. So you give it some data sequence and it will make a frequency dictionary for you automatically. So, and we're going to learn a little bit about default parameters, passing default parameters as arguments to Python functions in the process. Okay. So remember, if we just put 1, it's in Sage Math, 1 or 2, these numbers are just Sage integer things, right? They're very heavy. So maybe we don't want to use a Sage rings integer to keep the counts, because it could be a lot of overhead. So we want to pass in a default value for 1, because when we count lots of things, we have to start with 1, right? And keep adding 1. So here's just a recall. So Python has integers and long integers. And unlike Scala, where the max value differs, last night I was looking into Python docs, and it says that the Python integers, at least in this Stack Overflow thread, which seems reasonable, Python integers will automatically switch to longs, and then longs will get arbitrarily big as you need it, apparently, up to memory. So they are doing something under the hood when it goes beyond the standard size. So, but still, it'll be a lot lighter overhead than using Sage integer rings for counting. So then, so yeah, here's how you write a Python integer, long integer, long of 1, and so it'll be of type long. And if you use type of 1 directly, it'll be the Sage rings integer. So what I would like to do is to have this makeFreqDict function, which takes my data sequence and then has this parameter called ONE for 1. And I'm going to declare its default value to be integer 1. Okay? That means if I don't specify the second argument, this Python function will be very happy using this default value of int1 for ONE. Okay? But this gives me the flexibility of changing this to long of 1 or, you know, or QQ of 1 or whatever if I want later. So what am I doing? I'm basically starting an empty dictionary called freqDict. Remember, this is how we put this curly braces for dictionary. And then now I'm going to march through every res, which is like a result or item in my my data seq, which is the input sequence of items that comes to me. And then if this item is in the freqDict already, then I simply increment its value. So I say freqDict of res equals freqDict of res plus ONE, right? Which will be integer 1 by default. So if I already have it there in the dictionary, then I have to increment its value by 1. If I don't have it there already, then I have to initialize its value to 1 to be 1, right? So it's easy peasy. So that's just the heart of counting, right? In the dictionary, data structures take all of the stuff under the hood for you. as long as the sequence that you're passing in is hashable. It has some order. So this is a little example. My example data list is 1, 2, 2, 3, 3, 3. And then I can just call this function make free ticked on my list. And it will tell me there's 1, 1, 2 2s, and 3 3s. Okay. So if I do another 3, just say there are 4 3s. Okay.
Why do you write like 1 with letters and the number 1?
Oh, because I want that to be a variable. And, oh, variables cannot begin with 1. Variables cannot begin with a number. I'm just calling it my OID. So I can pass it in 1 or whatever one I want. So for example, if we do this, make free dict of my example data list, comma, long 1. Well, I'm going to be really crazy and say my long is 100. It's my incrementer. Okay, so yeah, now I can get the items in the dictionary. So that'll give me tuples. I can just get the keys, I can get the values. This is recalling dictionaries from last week. Yeah, okay, this is what I did. So I can do long 1 if I want, or int 1. And I can also pass in the sh integer rings 1 as well. It's fine. I don't think it matters this smaller list. But okay, so my example data list. Yeah, so they're just returned as a dictionary. So I can ask if this thing, my example freak int dict, and this one that's done by default, are they the same? This should be true because that's what happens by default. Right.
What if you check if the one with a long is the same?
That's a good question. Let's do it. It probably, I don't know what it does for equality. Yeah. Now you know. Because for it, I guess a long int is the same as an int. But it's not type checking. Good. Okay. My example freak int dict. Yeah. So here's another example. So now we take a NumPy array and then feed in the NumPy array. This is fine too, because it's just going to iterate, march through the sequence. NumPy array is a sequence, no worries. How about a string? Yeah, no worries, right? It's going to march through each element in the sequence, which is our string. And we can do with Unicode strings and whatever. So it's kind of pretty general. So in fact, a lot of my research the last couple of years, that's more combinatorial, I use exactly this function to count the occurrences of so-called transmission trees. So somebody passes a disease to somebody else. So this is say individual 2. This is individual 1 passes to individual 2, and then individual 1 passes it to individual 8. And so on, and this is a so-called transmission tree. People study this in epidemiology. And there's a whole field called phylogenetic epidemiology, I think. So these are people with lots of money where they study HIV sequences of patients. And so you have a contact network of who has sex with who, basically. And the same thing for drug users who all are in the same syringe sharing bin. and then they may get some disease through the syringe or through sex, and then it becomes very important to try and understand who transmits it to who, purely based on the HIV DNA sequences that are inside the hosts. So then what they try and do is from the DNA sequences, they can reconstruct what's called a phylogenetic tree, some ancestral relationship, yes. And then this tree itself is going to depend on, say I1 is like our super, who's this Italian guy who's had a lot of girlfriends? Sorry, this is
I mean, you could make some sort of...
No, there's this famous character, right? What is this? He's very likable, let's say. So, okay, so if this is called a hub in a whatever contact network. Trump is like this, right? In Twitter, Trump is very popular. So again, retweets can be considered as transmissions. So what's the point is the shape. I mean, this is just a simple star shape, but that can be a more complex shape. Maybe this guy has his own little pod here. This guy's super fancy. Whatever. So, it's a very arbitrary structure. And then the shape of this tree is a very complicated combinatorial function of the shape of the contact network. So, and exactly all this stuff I'm telling you, just dropping into the Sage graph library and the Sage tree libraries are already implemented, it's almost like 6 blocks of code. And you will get a sequence of transmission trees as a function of the contact network, and you can use exactly the same dictionary to count how many trees of a certain shape happen. So you're just dropping right into modern phylogenetic epidemiology. I don't know. If I had like one more full day, I'd probably take you guys there. Let's see, maybe. Okay, so now what I've done is just counted what is the frequency of each of the balls in my New Zealand lotto, right? So 40 occurs 37 times, 1 occurs 29 times, and so on. So now what we want to do is, how do we plot this? How do we try to make sense of this? And this is data from 1987 to 2008, New Zealand lotto draws. So I'm going to try to get a bit more into points. So we already saw what points are. And let's look into lines. So this is another graphic primitive. So line basically returns either a 2-dimensional or 3-dimensional line, depending on the value of the points that were passed to it. So I just can give it a pair of points, and it will plot a line between the pair of points in 2D. I can give it a pair of 3 tuples in 3D, and it will just plot a line in 3D. So points, lines. Okay, you can do quite a lot with points and lines. That's what I'm trying to do here. So what are we doing? We're plotting. So here's my, so I create a variable called lotto plot counts, right? And I'm initializing that to be the point. And this is essentially the items. Remember, ball 1 freaks items. Let's just take this apart a little bit. So print ball 1 freaks dot items. So that guy is just going to give me all the items in the dictionary, right? 1 occurred 29 times, 2 occurred 28 times, and so on. So that's the input to this point thing, right? So that's, and I'm going to call this RGB color red. So it's basically going to make this first image of points. So for example, if I comment out this extra bits, I should just see the red points, okay? With X and Y tuples thrown in. That's nice. But then what I also want to do is I want to throw a bunch of lines, because I want to formally look at a probability mass function. So then I'm just putting lines from the bottom to the top, so in dotted blue. Okay, so this is essentially called the empirical mass function up to normalization, just the frequencies. So that's a statistic. The next one is empirical mass function. So you just divide it by n, right? This is the frequency statistic we just saw. If you divide it by n, it becomes a mass function. So once again, with list comprehensions and tuples, we can do this. And all I've done is, you see, I've taken, it's the same as before, but now my function, make EMF, makes an empirical mass function from a data list. So it first uses the make freq dict to make the frequency dictionary, and then it creates a variable called total counts, where it converts the sum of the freq values, because it only looks at the values, and then it's the sum, and then turns into a MPFR multi-precision floating point reals using this RR thing, because otherwise I'm going to get integer division, right? So, and then I just now do a list comprehension where I say rel freaks is this list, okay? List comprehension, where I take frequency FR in the frequency values and then simply divide it by the total counts. Then I do the zipping, right? So we saw zip before. So I can take the freq keys and their relative frequencies and zip them and get this 2 tuples. And that's it. And it just returns it. So, right, so if I, and then now I'm just going to plot it. Nothing going on. So this is just going to be a normalized version of the frequency plot. Okay. This is called the empirical mass function, because the empirical mass function, in fact, is a non-parametric, it's an estimate of the probability mass function, the true probability mass function itself. Okay, because I'm taking the relative frequencies, normalizing it. So I'm taking the frequencies, making them into relative frequencies, and that is basically the guess of what the true probability mass function is. So then we start looking, okay, this kind of varies between 0.02-ish to 0.03. Maybe the de Moivre random variables probability mass function is not a bad idea after all. Anyway, here is the mass function for the de Moivre random variable, right? Frequencies are all 1/40. So now I just have to zip it with the keys and print that. So now I'll have, you know, these tuples, 1/40 for every second element for each of these entries. And I can just plot that next. So I'm plotting the purple dots with the blue lines, which is the empirical mass function. And then I'm plotting the de Moivre equiprobable 1/40 random variables mass function, the green dots. So that's the probability model, and then the empirical mass function is the statistic from the data. So that's kind of your first look at how well the probability model at least matches up to the mass function. Are you guys okay? Okay, the next statistic is called the empirical distribution function, or EDF. So this is kind of the Mac Daddy, right? So remember, a real valued random variable is completely defined by the distribution function, right? So this guy actually, just like the empirical mass function is a natural estimate of the probability mass function, the empirical distribution function is a natural estimate of the true distribution function that the random variables are coming from. So this is how you think about it. It's defined like this. You put a hat, and in statistic, the typical thing is to put a hat on top of something, which means it's an estimator. So yeah, and then you subscript with n because there are n samples, right? So.
From minus to infinity. Like why are you counting?
Oh, the indicator function.
Yeah, it's from x to y to plus infinity, but
yeah,
we were defining the distribution function.
Yeah, but it's adding the steps forward, right? So, I mean, what is that? So it's just saying that So for a particular value of x, whatever it is, the empirical mass function is defined to take the value 1 over n, or of the indicator function of, these are random, right? Capital Xi are actual data points. So let's say in this example, only 2 points fell. So this is my, one of the points, the random points. Then it's just saying, and so 1 over n will be 1 over 2. So let me do a 1 over 2 line here. And then I will do another 1 over 2 line here. There's another 1 over 2 line here. But I have to add them. So this will become, 1 over 2 plus 1 over 2. This line moves up, right? So that's the empirical distribution function. It's a step function. Yeah, you add forward. Because yeah, it's a little counterintuitive. I was getting confused with this as well because you look at the another way. Yeah. Okay, so now let's make a function for this empirical distribution function. So it's the same thing. It takes my frequencies from the make free predict, and it also does the total counts. And this is all the same as before. It takes the relative frequencies. And now I'm going to turn this into a Numpy array. And I'm using this cum sum. We will look more into cumulative sums later, but right now it's somehow doing this cumulative sums of these constants. And then I zip it, and I return this num frequency pairs. And then here I'm going a little nuts. And I am going a little nuts on purpose. So I didn't want to just do a step function like MATLAB will give you stairs, because I'm going to make this smaller. Because that's the whole point, is that you need to understand what the holes mean and the filled holes mean and the dots mean, right? Because these are jumps. So these are functions that are called cat-like functions, right? What is it? Left continuous with right limits? Yes. Yeah. Well, okay. So, what that means is just that
right continuous with left limits.
Yeah, so right continuous means, so when I come from the right, you have to understand limits and continuity and so on, but think of like a rabbit just jumping like crazy, approaching a point from the right, and then I look at the image of that hop. That's a sequence. And if it's approaching a particular point, then I need to make sure that the image sequence corresponding to these jumps downstairs is going to be the value taken by the image of the limits. So this is how you define continuity. So if you come from the right, the function will appear continuous. Okay, that means the image of the limiting point downstairs is the limiting point of the image sequence upstairs. But then if you come from the left, this is not guaranteed. Because if it's not a left continuous function, that means you can come from the left to this point, right? But then there's a hole here, right? This is an empty circle. That means there's the value is actually there. So if you come from the left, it won't be continuous from the left because the image sequence upstairs for the final limiting value is jumped up, right? So this is a very, very large class of functions. In fact, distribution functions live here. So this is, you can do proper empirical processes just working in this space. And it's, even more interesting, right? This empirical distribution function, you get to this, called the fundamental theorem of statistics. It says that with n data points drawn from some distribution, no matter what it is, right? It can be any distribution function, absolutely any, right? In the space of uncountably many ones. The empirical distribution function will converge to that unknown thing when n gets large, no matter what. Very powerful theorem, and it even has rates of convergence. So anyway, it's one of the most important statistics. So now let's do real-world data ingestion. Okay, so I don't know, I was getting bored with the New Zealand Lotto data, so I was just looking around for other. So this is a data.gov US site, and this is lottery Powerball winnings. So you know, there's a comma-separated variable file that you can download, and so that has all the Powerball. So if you do this, you know, from URL lib import star. So this is a library Python for mucking around with URLs. So you can just open this URL open. Okay, and I know this is the command you need to do in the website download, and then you can read, and then you can decode it into UTF-8 and create a list. I don't know. Let's see what happens. So we're not storing any files anywhere. We're just going, grabbing, and doing it. Okay, so it's already done it. It says type Unicode. Okay, so now, I mean, I can look at what is in NY Powerballs, but I know that it's this long string, right, of the whole file. And then it has this /n, which is the end of file character. So I want to split it by the end of lines. So I get like every row into its own. That's what that should do. And so what that returns is a list. Okay. So now I can look at the first 10 entries of that list. Yeah.
Get some error when I try to load the.
What does it say? Too many requests or something?
Unknown type.
Just remove the HTTPS and put HTTP.
Okay, try that. I don't know. Word.
Yeah, that works.
Okay, that's good. Oh, interesting. Okay. So that, and then yeah. So we're gonna now process data, right? So this is now my list of end of line split strings that we sucked, and then we can ask how many are there. Okay, it's still 866. It was 853 a little while ago. So then now I can look at the first row, right? Remember, the 0th row is just the header telling you what the file values are. I didn't want to like do all this table magic and just tell you guys how everything comes into some nice Python package thingy. So let's just do it like with strings, right? So that's my first, you know, 0th element of the list will be this thing. I don't want it. I'm just grabbing the data itself. And that's what I see. So I notice a comma here, and then another comma here, right? And so these are the winning numbers, and that's the draw date, and then I don't know, multiplier is something with log Powerball, I don't know. So that's great. So now what I want to do is maybe I want to split it by comma. Okay, so let's just play with this first row to understand the data a bit. Okay, I split it by comma, and now you see I have these 3 comma delimited elements as their own Unicode strings. So then I want to grab the winning number, so that's the index 1, right? The second element. So I can grab the first row's Powerball winning numbers. So now what I'm going to do is I actually just want to, you know, grab each integer separately, right? So I take this stuff and then I split it by white space because I notice there's white spaces separating them. So that's all I've done, separate further by white space. Then what did I do? So then I said, okay, let's just grab the first element of this list with the 0 index. So that's my first Powerball out of this, right? That's similar to this New Zealand Lotto thing we were looking at. Okay, so now what I want to do is I want to cast that Unicode string into an int, into Python int. So I now have like integers, right? So you see I've taken my string somewhere from New York and then I have random variables already. Okay. So now we can just apply this expression and loop, right? So I'm going to have my array called first wins, and it's initialized as an empty list. And then for line in New York Powerball lines, that's my my string. That's already been split. I'm just going to cast everything into an int, the first one, and I'm going to call that win1. And I'm going to just append win1 to first wins. Oh, there's an error. So I mean, I did this exactly like how I processed, right? So I noticed this error. I said, oh, what's going on? So it says invalid literal for int with base 10 winning. Okay, that's easy, right? Because remember the first row was just the string. So it's just pulling winning out and converting it to an int. It can't do that. So yeah, so we just have to skip that line. Okay, so what we're going to introduce you to is the try and catch framework for fielding errors gracefully. So yeah, so here are the docs. We can dig into it, but quickly from the docs, the try statement works as follows. So first, the try clause between the try and the except keyword is executed. And then if no exception occurs, right, so some sort of error, the except clause is skipped and the execution of the try statement is finished. If an exception occurs during the execution of the try clause, the rest of the clause is skipped. And so let's just see this in action, right? So here's exactly like before, except now I had a try and an except statement. So I'm going to try, I put a colon after this keyword try. I'm going to try casting this win1 into an int like before. And then if that succeeds, I will be appending it. Like, okay, this is my full try. And then if I can't, you know, there's a, that can be done, then I'm going to have this except thing I'm going to call value error. And then I'll say error numbers only was whatever. So that's going to be my next try at it. So it gave me this error only once. It's for the very first thing, no, very first. So it kind of gracefully marched through now, right? So it gives me first wins 17, looks good, 14, and so on. Right? So let's make sure at least the first one is correct. Right, so the 14 will be the first Powerball in the next row and so on. Okay, so now let's sort of bravely process all the lines. So because I only tried the first 10 here, right? So let's go. Let's see what happens. Oops, another error, right? This one says list index out of range. So it's a new error, some kind of index error. So what's going on? So so I want to first look at the length of this list that it has processed. It's up to 864. And so this will grab the 864th entry. And then if I look at the length of the actual list, it's 866. So something happens in the end, right? It's sort of processed a bunch of stuff. And then, so what's going on? So let's look at 865, which is now the last row. And voila, New Yorkers leave the last row empty. That extra end of line, you know, they have like an empty line. I don't know why. So, well, that's easy. So what we're going to do is add another except, okay, clause. And this time I'm going to call this index error. I don't know, you can call it whatever. And the list length had index error line. So Yeah, so just, yeah, the line was nothing because that line is empty. Okay, it's the very last empty line. So now we can find out what's the length of the first twins. It's 864, that looks right, right? Because we don't want the very first row, which is the header, and the very last empty line row. So 866 minus 2 is 864.
Why the empty line was not cut by the first step? Like, why did you need another one? How?
Because it's a different error. Okay, the reason, because what it's taking the empty string and then it's trying to, because we're trying to access it takes the empty string, it's trying to split by comma, and then it's trying to split by white space and trying to access an element. So I mean, it doesn't have these things, right? So that's why it's getting a.
Yeah, but I don't understand why the second one fixed that problem. Like, why different from the first one?
No, we just basically say. We just basically say that, because, if yeah, it's the error type, right? So we have value error and index error, whatever error pops out. So,
okay, so that's.
yeah. Yeah, I mean, I don't know, there may be some other error, right?
Can I ask you something?
Yeah.
How is the error handling in stage math? Is it very time consuming? Like would you prefer to do error handling or just check that the line has any figures in it, or I
think stage math is just like a superset of Python, right? Yeah. I mean, it's just,
yeah,
so if you can use classic Python, most of the stuff is written in Python. But sage math has it's kind of like R, it includes R as well. So it depends on what part of it you're using.
I mean, say if you have a file with 10 million rows and every second row is blank, and you have to do like this exception handling every.
No. I mean, I think if you have multiple blank lines, you don't have to redo it because that error will again pop up. It'll still give me an index error. So any index error will be handled, right? If I arbitrarily insert blank lines into this thing, it will it'll.
Yeah, but I mean the error handling itself is in some languages it's very time consuming. So you wouldn't have an error handling in a for loop, for example, because it takes more time than just checking if the line is correct or just doing by length of the line.
I mean, this took me like maybe 7-8 minutes, this whole process, and I actually didn't know too much about Python try-catch, so I read the docs as well. So I don't know. I mean, that's a hard question to answer, like in generality, right? Like, I don't know. It depends on the problem. And in fact, I have a live file we will process together. I purposely didn't do this. We'll see what happens, right? I think it'll be a better exercise. That's on New Zealand earthquakes. And I didn't even look at, yeah. And I'm not a programming nerd. You should really take a Python course. This is kind of like just enough Python to learn maths. So, and I think Tilo knows a lot more about programming because he did a double major in basically computer science and maths as undergrad.
I'm not sure how much programming I learned during that, but.
So yeah, I actually don't know, and yeah. Okay, so basically whatever error pops out, you can just do an accept and handle it somehow, right? There'll be more delicate handling as well, right? It depends on what you want to do. But for us, we just want to just do this. So we're just printing the first 10 elements and then the last several elements, and it looks like it's okay. They're all integers like we want. So I wanted to say that congratulations, you've taken your first step towards being a data scientist. And that's the point, right? We kind of want to track the data from source and not just do statistics and maths and programming. We kind of want to. Well, anyway, that's at least the idea. But I want to point out that here I'm kind of helping you take the first step towards being a mathematical, statistical data scientist. These are just words, right? But what I mean is I want you to be comfortable with this axiomatic notion of probability. Think about what is really under the hood when you make probabilistic statements, because it's just a language. It's an axiomatic system. It's just a construction, right? So you need to also be aware of the fact that this is actually just a la-la land in cartoon called mathematics in your head, right? And you need to be able to question it and challenge it. And that's very, very important. That's what makes you a very good scientist or data scientist at the end of the day, right? Yeah, but often that's good enough. So a lot of clever people have worked on these problems for a long time. So, and finally, computational mathematical statistical data scientist. I just throw this other word in. That's why we're getting into, Python, and we'll do a bit more. So you also should be quite brave and just get into computers and do stuff. And also, yeah, the other thing I really recommend is you really need to not be a kind of an arrogant guy or a girl or whatever. You have to work with domain experts, and this is the whole point. There's no way, at least the people that sort of talk about data science, they are not saying you can do anything. That is just crazy, right? You have to work with domain experts, like people like John or the guy from Umio, Simon, because they are experts. They know what's going on. I mean, you really have to work with them, and that's about 1/3 of data science is about domain expertise. And of course, I have my own little domain expertise in this tiny corner of population genetics, but that's because I spent decades getting into it, right? So I usually think I know some of that stuff, at least the modeling end of it. But then I have to work with other people if I want to make progress and listen to them. Okay, so let's do arrays. Yeah, maybe I should do this faster, okay? So let's try and crash this notebook before lunch, and then we can come back with more stuff. So arrays are essentially our main friend here. So we're going to use Numpy arrays. So now we just import Numpy as NP. And so what I'm going to do is create an NP array by giving it a list of lists. So this is one way to do it, right? So I'm just making it a list of lists, and then I'm asking what is this array 1. This is to make an array kind of the hard way. I can ask what's the shape of an array. So it's a 3x6 array. So this is another way to make an array. So you can just do int of I for I in range 18. So I can make a 1D array using Python ints. And then I can turn this in, I can resize it. So resize is a way where you restructure the shape of the 1D array. So this has 18 elements. So 6 times 3 is 18. So I can resize it into 3 rows, 6 columns like that. Okay. And then the type array 2 is, now if you ask what is the type, it's a NumPy ND array for n-dimensional array. So this is the fundamental thing you need to work with. But TensorFlow, how many of you know of TensorFlow? Okay. So TensorFlow is sort of, when did they release it? Like last year or something. I don't know. I just remember reading something in LinkedIn and following some links, and boom, like in 2 months, like it was an explosion of. So TensorFlow is Google's open source library for machine learning. So they open source their entire, or a large part of their non-hardware artificial intelligence stack. So everything is free. It's all C++ code, but with Python wrappers, and so you can do speech recognition, or you can even train a bot to have a conversation or whatever. So there they work with their primitives. They work with are called tensors. The tensors are essentially multi-dimensional arrays. So TensorFlow is about tensors flowing on a graph, directed acyclic graph. There's also called deep learning. I don't know if you know these words. But yeah, that's what's really under the hood. And if you take these courses, I took some courses in Udacity on TensorFlow. They do all the first concepts using NumPy ND arrays. So you roll all your algorithms from scratch using NumPy. So here, what I've done, I've resized it with 3 dimensions. So the first one has 3 elements, second one has 2, and the other one has 3. So you can get multi-dimensional matrices or whatever, tensors in general. So then this is a nice function called arange for I don't know, array range. So just like a range function, it's a Numpy function. So it has arguments start, stop, and step. So remember when I plotted the points for the Bernoulli random variable, I had to divide by multiply by 0.01 because I was only using integer range. But with NumPy, you can just do a range and directly get numbers starting from 0, ending before 0.18, and increments of 0.01. So it's a nice function method. A range, then you can ask what's the type of array 3. It's still an ND array. You can ask what's the shape. Right? This is a one-dimensional array, 18, and we have to put a comma if it's a 1D shape. Later on, we will see how tuples, one-dimensional tuples, behave. So it's one of these things. It's because the shape just returns a tuple. This is a 1D tuple. Now, resize and reshape are other convenient methods. So, which can resize. Let's say we take our array 3, which had 18 elements, and we can simply resize it into a 9 by 2. And then we can ask what's the shape. So the shape is now going to be 9-2. So this is an in-place reshape. Or I can take array 3 and reshape it again into 6-3. It's the same numbers. And now my shape for array 4 is 6-3. But array 3 remained the same because this did a copy first and then. Okay, so we will use these later on in various functions, so it's just mostly syntax. So now indexing, slicing, and copying is also straightforward. So let's create an array, array 4, resize it, and display it. So now array 4 of 0, 0 is the first element. Array 4 of 5, 2 is this element, right? Fifth row, last column. Index 0, index 1, index 2. Makes sense. And so if I do 3, it should give me an index error. Okay. So now we can use colon specifically to give the ranges. So now this is going to grab me from 0, 1, 2, 3. Remember, 4 is not included. So it just gives me the first row. Right? So that's what that is. Just the first column. Because yeah, it picks these rows, and the 0 is the first column. Oh, I'm getting confused. Sorry, what's going on?
The first column, the first 3 rows of the first column. So you only do 0 to 4.
Oh, right, sorry. Thanks. I need to eat soon. Okay, so yeah, I think I wrote it right. So anyway, it's kind of boring, right? I don't know. This is also useful, right? You just grab the second row, all the elements. So everything in the row, first column, so on. So the slicing is nice. Okay, so to play with this, and so this is very important. We want to take copies of the array. So if I do array 4 colon, just a single colon, it will make a full copy. And we saw this before. And then I can resize the copy. And my original thing I copied from was left alone. So here are some useful arrays. So np.zeros, np.ones.
Sorry, a very quick question on the copy. What's the difference between keeping that and removing it? You will get the same, the brackets and the column. Is there a difference between the two?
So
if you just remove the brackets, the square brackets, and the colon, you will get the same result.
Yeah, but I think this goes into this Python weird thing. I don't know, I don't know, naming things. This is how like you're supposed to copy in Numpy. I don't want to get into like stuff.
Yeah, because if you change your code, it will also change this code.
Yeah. Remember we talked about it in the single variable case. Python has this strange behavior when you copy. So this is what you're supposed to do when you copy arrays. Just, it's like the C thing. So the last 5 minutes, let me see. So yeah, zeros is nice, ones is nice, identity is nice, right? This is the identity matrix. So later on, we will see that this becomes the variance covariance matrix of a multivariate normal or Gaussian random variable. Here are some useful functions for sequences. So sequence, now we're going to deal with lists and tuples and other sequence containers, methods that are useful for them. So you can convert a list into a tuple by simply calling tuple, right? So this has parentheses, this has square brackets. Then we have observe data tuple.count, which is a method. So it counts the frequencies. So it's nice to directly use the count method on tuples. Here is the sum. Once again, divide by 3. So this is doing Sage rational arithmetic. Yeah, so you can count. And so this is another way. If you have just tuples, you can do these relative frequencies directly using built-in methods for tuples. So here is the same thing. I'm trying to explain what was inside these functions we were sort of looking at earlier. So I'm just sort of taking the function apart. This stuff we use to plot the empirical mass functions and distribution functions and so on. So this will just make more sense because now you have a better understanding of all the different pieces. So this is something about tuples that sort of is good. I can define an empty tuple with just these parentheses, and then the length of empty is 0. And then this is a fine singleton tuple. So I can put 1 comma. This is because if I just put 1 in a parentheses, it just is going to be an integer, right? It's an expression, right? So this is something that will mess you up. If you want that to be a tuple, you have to put a comma space. And an unfined single tuple, right? That's still an expression. Here's a lonely string, same thing. Here's an unfined lonely string because now it's not a tuple, it's a string. So you have to put this comma here if you want a singleton tuple. So now I have my tuple of stuff. I can have different types in tuples like Python land. So I can have 1. This is my Sage integer, Sage rational 1. This is the Sage multi-precision floating point real 1. Python integer 1, Python long 1, Python float 1. So this is all the different ones we've seen so far. Yeah, 1 is ZZ of 1. So these two are the same. Our Sage does type inference of 1. My tuple 2 is this guy here. So I can do assign a tuple to a variable named my tuple by simply putting a comma even without the parentheses around, because then it type infers that to be a tuple. Python does this nicely. So you can save some typing. And then this is called tuple unpacking. So I take my tuple and then just do x comma y equals. Then it will take the first element as x and the second element as y. That's tuple unpacking. Okay, so this is just unpacking the packing. So now I'm just basically marching through this, so mimicking a for loop. So this is what we saw as list comprehension before, right? It's just this for loop thing. But what if we do this? We will break for lunch in the next 10 seconds. So I'm doing list comprehension.